All right, so back into our OneNote. So got two problems with two different parts. So the first part will be review, and the second part will be the new part of chapter 7. All right. So then this is a problem out of the book. So a Gallup poll has 1,011 adults were asked if they consumed alcohol beverages, and 64% of them said that they did. Construct a 90% confidence interval of the proportion of all adults who consume alcohol. Right? So, what type of confidence interval are you doing?
Wouldn't this be the one we did last class?
2 classes ago.
The critical value?
Well, critical values are for all of them. So what is the key word here?
Proportion.
Proportion. That is your key word. We're doing a confidence interval on the proportion. So if you go to your pullout, we have the formula. P hat minus E is less than P is less than P hat plus E, right? So that's the formula we have to use, and I know this because of the fact that it says it is a proportion problem. So now we go through and we start highlighting all of our key pieces of information. We have 1,000 adults. 64% of them said they consume alcohol, and we're building a 90% confidence interval on the proportion, right? So now let's start labeling things. We know N is 1,011. We know P hat because 64% of the 1,011 are who said they consume alcohol, so that means it's a sample proportion, so that's P hat, and that is 64%. And then if 64% said they do consume alcohol, then that means 36% do not, right? Because P hat plus Q hat has to equal 100%. So that's what we do know. So I'm gonna erase my, well, I'll leave my formula there. It's okay for now. I just have to give myself more space. So if I build my bell shape, because it's a proportion problem, and every time a proportion problem, it is a Z, right? Because we got to find our critical value for our E formula, which is the Z alpha over 2 square root of P hat Q hat over N. Let me get out of draw for a minute here. Give myself a little more room to work. So we have to find our critical value, right? So break up my distribution here. I'm doing a 90% confidence interval, so that goes here in the middle. And then I got to find my Z alpha over 2, which is that guy and that guy, right? So what is my critical value? So remember, to find that,
10%.
if there's 90% is inside the thing, that means my tails, I heard someone say, is 10%, which means each tail has 5%. So I have to go into the table and find 5%, which gives me what value?
1.646.
1.645. So a negative over here, this means there's a positive on this side. So my critical value is a positive 1.645.
Why is it 4, 5, and not 6?
Where do you see 6?
So
I had the 6 too, 1.646.
at 1,000, underneath that column, it goes to 1.646. If it's larger than 2,000, then it goes to 1.645. It says on our chart.
Oh, we're not. You guys are on the T then.
Oh, oopsie.
We're supposed to be on the.
Yep, I'm on the T.
Me too.
Supposed to be on the Z.
Okay, well, I'm on the T.
Yep. Z for P.
Z. There's too many letters. Math should not have letters. I'm just saying.
But it still would have been okay if you did use the T because you're only off by 1,000th, which is not going to affect our calculations any.
So where would we find it on the Z?
So you'd find 0.0500, which on that spot is a star.
Yep.
You follow the line down and you see it says a Z-score of negative 1.645.
Yep, I see it. Okay, thank you.
Yeah. So now we can start putting things into our formula. So first we'll solve for E. So E equals 1.645 times the square root of 0.64 times 0.36 all over 1,011. Which is 0.025. Yes, no?
The baby ran off with my calculator, so I'm going to trust that you got the right answer.
I just had my calculator. Now I don't know where I put it.
That's what I got.
Okay.
How about this? I ended up with 2. After she took 1, I got 2.
Maybe
There
she
you go.
has mine.
Okay, hold on, Tammy. I'll send it right over.
Thank you.
So, Chris, it's 1.645 times the square root of, and then all that, right?
Correct.
Okay.
So we then take our formula for a confidence interval and we take 0.64 and minus 0.025 is less than P is less than 0.64 plus 0.025. It was taking up way more room than I thought with drawing here. So that will give me a lower of 0.64 minus 0.025. So a lower of 0.615. And an upper of 0.665. 5.
I don't know what I'm doing wrong, but I'm not getting that.
0.025.
Probably the way I'm typing it into the calculator.
Yeah, so if I'm typing my calculator, I want to hit 1.645 times,
Yep.
then find your square root symbol,
Yep.
0.64 times 0.36 divided by 1011. And that should all be under the square root, and then just hit enter.
Ah, now I got it. Thank you.
You're welcome. So to finish this out, I am 90%, because that's what kind of call so yep, 90% confident that the true population proportion, are we building, of adults who consume alcohol is between 61.5% and 66.5%. So that one's a review one. That's a review from 7.1. That's why I went not fast, but just kind of walked through all the steps again. So hopefully that was a little bit of a review. Any questions on that one? Now, the problem in the book says, can we safely conclude that the majority of adults consume alcohol beverages, right? And this is where statistics comes a little more argumentative, right? So we're confident that the true proportion of adults is somewhere between 61.5% and 66.5%. If you can classify as something higher than 50% as a majority, then maybe you can say yes. If you think that's too close to 50-50, I would call it something a majority of higher than 75%, then you may say no. That's where statistics can get very argumentative. As you can see right now with coronavirus, with people arguing, do we open the economy or do we keep doing what we're doing? Right, so this is why we got to kind of
Argument would be those numbers are higher currently.
Yeah.
Of the amount of people who are drinking, stuck in their house, pretty sure.
Yeah. So we could also argue that the sample size is not big enough, right? To really say, hey, 1,000 adults when we have over 1 million people in the United States, that we might want to take a bigger sample. So any questions on how we got those numbers?
I wasn't laid on the mother pillow. It's hurting my hips though. I've got to lay down somehow. All right. Baby days.
Someone was not happy with the answer.
Oh, shit.
All right.
Sorry, I was just playing with my dog.
Now this goes into the new thing. So that's why I like this problem. So maybe the sample size is not big enough. So the other part of chapter 7, if you take out your pullout, is chapter 7, sample size determination. And when you look at that, you see there's 3 new formulas. There's 2 for the proportion and there's 1 for the mean. So what you use these formulas to do is, hey, I want to know where I would like my answer to fall. So how many people do I need to sample, or how many things do I need to sample, right? So I think the best way to kind of talk about these formulas is to apply it to a problem, right? So if we use the same problem as above, and remember, so we calculate our margin of error above, and we got 0.025, which is about a 2.5% margin of error, right? So what if I want to say, all right, I'm going to give myself a 5% margin of error. So you pick what margin of error you want. Up here, remember, margin of error is the E. I'm trying to find my draw again, right? That's margin of error. So we calculated it before. Now we're going to pick it ahead of time. So I know I want my margin of error to be 5%. And I want to still do a confidence level of 90%, right? How many people do I need to actually sample to get within that range? So the formula is, there's 2 of them. There is, and oops, I'll put my draw back on, draw. Where's my black here, people? I have n equals z alpha over 2 squared times 0.25 all over my margin of error squared, or I have z alpha over 2 squared times p hat times q hat all over e squared. So no new symbols today, so that's a good thing. The key here is what's the difference in the formulas? And basically the difference in the formulas is just this. If you know your p hat and q hat, use them. If you do not know p hat and q hat, use 0.25. And where the 0.25 came in is we assume worst case. Worst case. And the worst case is we are 50-50. And 0.5 times 0.5 is 0.25. So if you don't know your p hat, q hat, use the worst case, 50-50. If you do know your p hat and q hat, use them. And then everything else is, we already know, z alpha over 2, that is our critical value. And E is our margin of error. All of those will be given to you in the problem. So there is nothing to actually calculate this time. Well, your critical value you have to still find on your confidence level. So just like we did before, since we stayed with the same confidence level, we know our critical value is 1.645. This time, we don't have to find our margin of error. It's given to us. So our margin of error is 0.05, right? Using the problem from above, we know p hat was 0.64 and q hat was 0.36. So now I just solve the formula. 1.645. You must square it. We're going to multiply that by why did I lose my draw? There we go. 0.64. And we're going to multiply that by 0.36. And we're going to divide that by 0.05 squared. So now we type all that into our calculator. So 1.645 squared times 0.64 times 0.36 divided by 0.05 squared. And I get 249.38.
Yep.
Now here's the key. I'm going to actually type this in with big letters and even bold it. Always round up. So my sample is 250 people. I need to sample at least 250 people to have a margin of error of 5% and still have a confidence level of 90%. So this is something you could do if you're going to really do this in real life and you're like, hey, I want my results to be within this range. So before you actually go out and start sampling and talking to people, you can ask yourself, you can calculate how many people you should, what your minimum sample size you need to be. So our minimal sample size needs to be 250 people if we want to be within a 5% margin of error. And this is where you see this on the news where they do surveys and they always say our results are within ±3 or ±5. That's what they're talking about. They're talking about being within that margin of error that has been calculated. Any questions on how to find their sample size based off a proportion problem? All right, well, let's do another problem then. So, a random sample of 25 chocolate energy bars have a certain brand has, on average, 330 calories with a sample standard deviation of 15 calories. Construct a 99% confidence interval for the true mean calorie count of this brand of energy bar. Assume that the distribution of the calories is approximately normal. So, what type of problem is this?
Confidence interval of the mean.
Confidence interval of the mean. Yeah, this problems in this chapter will tell you exactly what formula to use if you look for the keywords. So I am doing a confidence interval of the mean, which means I have to do a t distribution.
Oh, now I can
So-
look at the chart?
Yeah, Z is for P, T is for mean. So we look at our confidence interval of the mean and we get a X bar minus E is less than mu is less than X bar plus E, where E equals T alpha over 2, S over the square root of N. And that's how I know it's a T, because the critical value has a T in it. So we have a T, so I draw my limits. I put in a 99%. Therefore, my tails is 1%. No, fix that. 1%. So that means there is a 0.5% in each tail.
Is it
I
okay
know.
to write 0.5 instead of 1/2?
You would have 0.05.
That's
I mean,
right.
sorry,
No.
0.005.
Okay.
0.5% would be, if I write it in decimal form, is 0.005.
Okay. Thank you.
And that's what I would write it as, because that's the number you're going to look for in the chart. Right? So what do we know? We have 25 chocolate bars, well, energy bars. We have an average of 330 and a standard deviation of 15. So now, what do we know? We know S is 15. We know our N is 25. We got to find our critical value. So we go to our T table. All right. We have to find 0.005 in one tail or 0.01 in two tails. So I am in the first column. I need to know my degrees of freedom. So my degrees of freedom is n minus 1. So my degrees of freedom is 24. So I come down to 24. I go into line it up to the first column and I get a critical value of 2.797.
That's what I got.
Perfect. And now it's just putting that into our calculator. So 2.797 times 15 divided by the square root of 25. And I get 8.391.
You're ahead of me. Just a second.
I'm stopping. I'm making room to write anyone. Because I don't want to move on until at least someone confirms my calculations.
What I got.
All right. I'll still wait on a minute though, but at least I know I'm on the right path this time.
That's what I got.
There we go. 2 for 2. So now I can plug that into my other formula. So again, I'll scroll up a little bit. So my average was 330. So that means I have 300, go back to my draw. 330 minus my error, which is 8.391, is less than my mean, is less than my average, plus, oh, not 300, plus 330, 330 plus my margin of error of 8.391. So I get a lower value of 321.609. 9 is less than mu, is less than 338.391. So I am 99% confident that the true average calorie, calorie count of chocolate energy bars at this company is between 321.6 calories and 338.4 calories. Scroll up a little bit here so you can kind of see my work for anyone that's writing. So this is 7.2. Questions?
So up in the E equals T alpha over 2, what does the alpha over 2 do?
Now it's just a symbol. That just means you take your tails and divide it by 2. Because remember,
Gotcha.
the symbol for tails is alpha. So I just wrote out the word tail instead of alpha.
All right.
But that's just saying, hey, we have 2 tails, so make sure you take your percentage in your tails and divide it by 2. Because alpha over 2 is equal to 0.005. Well, alpha is equal to 1%. So the T is, say, what is the critical value at that percentage? And that is the 2.797. Yeah, so just think of this as a symbol.
Gotcha. All right.
But it is a symbol that tells you what you have to do as well at the same time. And I said, and some students just don't like the symbols, that's fine. So you can just write tails divided by 2 if you like. Just whatever makes it easier for you, I am fine with. I am so worried if you know the symbols. It's more of what the symbols represent. So great question. Oh, it's my answer. Okay. I was like, what is that writing? So what's your answer? All right, so no questions? Oop, that's not what I want to do.
Okay. Just to make sure I'm fully grasping this, say the confidence interval was like 95%. Does that
Yep.
mean the lower and upper limits would be closer to the mu?
Yes. So, when you lower your confidence interval, you lower your range here. So if we redid this at a 95% confidence interval, our numbers would be closer, right? So remember, this is not how accurate this thing is. This is how confident you are. And the reason the numbers are getting further apart is it's giving me more possible answers. So the more confident I am, the wider my range becomes. Because again, like statisticians, we don't like to be wrong. So by allowing myself a wider range, that gives a higher chance that my numbers are right, which is why I'm at a 99%. So when I do a 95%, my numbers actually, my range gets narrower, which then reduces the number of possible answers. So it doesn't make it more accurate because it will be easier to prove me wrong. That's what, so don't think of it just because we're getting closer, because we don't know what the true mean is. It could actually be outside of these numbers, but I'm 99% confident that it's not outside of these numbers. Does that answer your question?
Yeah, thank you.
Yep. Good question. All right. So what's wrong? Oh, I'm in draw. Like, why won't my thing screw? So here's the second part, which is the new part of chapter 7. So if we begin, so the company comes out and says, no, our true population standard deviation is 8 calories with a margin of error of 2 calories. So how many energy bars will I need to sample based on the company's statistics to construct at a 95% confidence level? So now we go to chapter 7 pullout, and we're again trying to find our sample size. So there's a new formula. So N, N equals Z alpha over 2 sigma all over my margin of error quantity squared. So notice on this one, my critical value is back to a Z. I am using a population standard deviation, which is that guy. And I am using my new margin of error of 2, which is that guy. Right? So I need to find my new critical value because I did change my confidence level. So if I draw my bell shape, and again, we're at a Z, so I know I'm centered here at 0. I want a 95% confidence, which means there's 2.5% here, 2.5% here. And now I gotta go find 0.025 in the table on the Z chart. So what do we get for our Z?
1.96.
Perfect. So my Z is 1.96. My standard deviation is 8. My margin of error is 2. So my sample size then equals, parentheses, 1.96 times 8 all over 2 quantity squared.
$61.4656.
Perfect. So just like before, we make it big. Always round up. So we need to sample 62 people. Well, not people, sorry. Get a sample of 62 chocolate energy enters and energy bars. And you notice before we only took a sample of 25. So definitely have to increase our sample size here to get a much lower margin of error. So the lower margin of error you want, the more you need to sample. The wider you want your confidence interval to be, then the higher your confidence level needs to be. Because again, we're not predicting how accurate our numbers are. We're predicting how confident we are in our numbers. So that gives me, the wider my interval, the more likely I am correct. But we want the numbers to be realistic, right? Like I could tell you that I believe the true average calorie count of this energy bar is somewhere between 0 calories and 100 million calories. And I'm 100% confident of that answer. But it really doesn't tell us anything. Like, duh, obviously it has some calories and it's probably got less than 100 million calories. So let's come up with a realistic number. And that's what confidence intervals are doing. They're coming up at least with some realistic numbers versus me just picking giant numbers out of air just so I could be correct. Any questions on anything we've covered so far?
I got one quick one.
Yep.
Even though the z-score is even though the z-score is 1.96, it's a negative though. Does a negative we just leave the negative as it, like we just get rid of the negative itself, or we?
Yep. The reason, because remember, this is symmetric. So when I'm on this end, that's a negative 1.96. When I'm over on this end, that is a positive 1.96.
Okay, so we go to the positive side. Okay.
Yeah, because they're both tails, because it's symmetric. Both tails are the exact same. So by doing just a 1.96, I'm covering both tails.
Okay.
The signs only tell you which direction you're going. If I'm a negative, that means I'm in the lower tail. If I'm in the positive, I'm in the upper tail. But I am still going 1.96 steps from the mean.
Okay.
It just means if I'm going left or right. When I'm doing this, it doesn't matter if I'm going left or right. It just matters that I've gone this far from the mean. Does that make sense?
Yeah.
Perfect. Any other questions? All right. So this is all going to be saved in my OneNote. So let me go home. I'm going to stop sharing my OneNote.